Chapter 20 Recursion, calling yourself over and over again. This chapter examines recursion, which is a method of solving a problem by solving a smaller case of the same problem. I give examples of recursion and explain how the computer can carry out recursion through repeated calls to the same function, but each time using a different, smaller parameter. In this chapter, examples of recursion, definition of recursion, key features of recursion. Recursion, what is it? Recursion is a particular process involved in solving a problem. Webster's definition of recursion states that it is a procedure that can repeat itself indefinitely. Essentially, a process involves solving a simpler problem of the same type as the original problem you were asked to solve. Let's first look at some examples outside of the context of programming to understand this process. Example using words. Let's say we have a vocabulary word whose meaning we do not know. Your second impulse might be to look up the word in the dictionary. Your first impulse might be to ask someone the meaning. Take the word obstreperous. If you look up obstreperous in the dictionary, it might say something like recalcitrant or willful. When you read this meaning, at first you will be happy that there is a word you understand, willful, but then disappointed that you need to look up another word, recalcitrant. So you next look up the word recalcitrant to see what that means. This time, the dictionary says something like defiant. At this point, you might think you know what defiant means, but you need to check it to be sure. So once again, you consult the dictionary, and you find that defiant means unruly. You're almost sure of the meaning of the last word, unruly. But you look it up to be certain. Here the dictionary says stubborn. See figure 20. Obstreperous, same process here. Recalcitrant, willful, and here, defiant. That is looking up a word, unruly, stubborn, base word. Figure 20.1. A word, obstreperous, is shown with other words used to explain its meaning. Each word below another word contributes to the understanding of the meaning of the original word. So, the word obstreperous at the base of all this work means something like stubborn, with some other shades of meaning picked up from the words along the way. Our process of discovering the meaning of this word has been a recursive process. We chose a method to solve our problem, finding the meaning of a word, by using the same process, looking up other words in a dictionary. Each time we look up a new word, we came closer to understanding the meaning of the original word. Recursion is this process of redoing a problem, but in a simpler context than the original problem we did. Consider the next example that uses recursion and involves numbers. Example using numbers. It is often easier to see recursion in a numeric example than in an example that does not involve numbers. In order to understand this example, we first need to define the factorial of a number. The factorial of the number is a product of the number and all the numbers less than it, all the way down to 1. The factorial of 6 is the answer you get from multiplying 6 by all the numbers less than it, 5, 4, 3, 2, and 1. Recall that multiplication is represented by the asterisk. 6 times 5 times 4 times 3 times 2 times 1. 6 times 5, 30. 4 times 4 times 3 times 2 times 1. 30 times 4 is 120. Times 3 times 4, 2 times 1. 120 times 3 is 360. Times 2 times 1. 360 times 2 is 720. 720 times 1, 720. So the answer is a factorial of 6. So the answer to the factorial of 6 is 720. Factorials quickly produce massive numbers because you are multiplying so many numbers, usually to get an answer. The factorial of a number is represented by an exclamation point. The previous example looks like this symbolically. Before we get to the recursion involved in the problem, let's redo the problem with some creativity. Let's start with the symbol for a factorial and use it in writing the multiplication form of the multiplication for the factorial. 6 factorial equals 6 times 5 times 4 times 3 times 2 times 1. Another factorial is here. The bold-face part of the preceding statement, which is 5 times 4 times 3 times 2 times 1, is another factorial. It is called the factorial of 5, or 5 factorial sign. Let's rewrite the previous statement using that information. 6 factorial equals 6 times 5 factorial. The previous statement means that the factorial of 6 is found by multiplying the number 6 by the factorial of 5. If we only knew the factorial of 5, we could finish this problem right away. So the solution to finding the factorial of 6 rests on our ability to find the factorial of 5, and then to take that answer and just multiply it by the number of 6. This way of solving the problem is a recursive method. We are solving the problem by solving a smaller case of that same type of problem. Now consider the separate problem of finding the answer to the factorial of 5. Consider what the factorial of 5 looks like as a product of numbers. Factorial 5 equals 5 times 4 times 3 times 2 times 1. Another factorial is here. Again, just as in the previous example, we can use another factorial to represent part of the work needed to get the answer to the factorial of 5. Let's rewrite the problem using that factorial. 5 factorial equals 5 times 4 factorial. And so the process continues like this. We find the factorial of 4 by finding the factorial of 3 and then multiplying that answer by 4. 4 factorial equals 4 times 3 factorial. The last two lines of work involve finding the factorial of 3 and the factorial of 2. The factorial of 1 is value 1. Consider these two lines of computation. 3 factorial equals 3 times 2 factorial. 2 factorial equals 2 times 1. Each line of computation involved finding the answer to a similar but smaller factorial problem. The important point to notice is that you are finding the answer to the problem using a smaller case of the same problem. The factorial of 6 used the answer from the smaller case, the factorial of 5. Another point to notice is that this process eventually stops. If it did not stop, then the recursive process would continue forever. Two features of recursion. In order to understand the topic of recursion more comprehensively, we need to look at key aspects of a recursive solution, or what constitutes a recursive solution to a problem. We will also examine how the previous problems, the words in the dictionary and the factorial problem, modeled these aspects. Let's examine the key features of the recursive problem. 1. A smaller problem of the same type exists. 2. Eventually, you reach a bottom case or stopping state. Recursion would be useless if it continued indefinitely. We would never arrive at an answer if that were the case. In the examples we completed in the previous section, both of these features were present in the solution of the problem. When we looked up the word obstreperous in the dictionary, we eventually found a simpler word whose meaning we did understand. The simpler word stubborn is a smaller case of the same type of problem. That is, the word is not as difficult as the original word. The stopping state for the word problem is finding a word whose meaning we do know, and then we can stop looking up words in the dictionary. With the factorial example, the smaller case of the same type of problem is using a factorial of a number less than the number we started with. The factorial of 5 is a smaller case than the factorial of 6. The stopping state is reaching a factorial whose answer we do know, the factorial of 2, since it is the product of 2 times 1. Infinite recursion is a problem that arises when one of these parts is not satisfied by the recursive design we make. For example, if we never arrived at a word we understood in the dictionary, we would always be looking up new words. Using functions in recursion. In order to understand how recursion works, we need to look at how functions are the bedrock of recursion on a computer. Imagine if we defined a function called lookup. This function would look up any word that we did not understand. First, we would call on it and send in the word obstreperous from the previous example. Then we would want to call the function again, but this time send in the word recalcitrant. We would want to call the function a third time, sending in the next word, defiant. The last time we call the function, we send the word unruly. We send in the word unruly, where the meaning we get here, stubborn, is clear to us, so we can stop calling the function lookup. The process of looking up one word and then another and another until we get our word whose meaning we know shows that we need to make several calls, 4 calls in fact, to this function. See figure 20.2. Figure 20.2. A chain of calls is shown with a new word sent to the function each time. Look up obstreperous, look up recalcitrant, look up defiant, look up unruly, and the arrow points to stubborn. Okay, I get it, stop. One function calls itself. The reality behind these repeated calls to one function is that the calling occurs within the function itself. Now what does that mean? I have always talked about the main program, the main function, making the calls to the function. In reality, any function can make a call to another function. In the case of recursion, the function calls itself. Let's see what this does. In the lookup example, the main function calls the lookup function and sends in the word obstreperous. Once the lookup function starts its work, looking up a word in a dictionary, it finds another word it does not know. So it leaves in the middle of its own function and calls lookup again, this time with the new word it did not understand, recalcitrant. The idea behind the call to the function is that once it understands the new word, it can use that knowledge to understand the meaning of the first word, obstreperous. How recursion is executed. Recursion is dependent on the ability of a program to call a function over and over again. The first step in recursion is to define a function that will solve the first case of the problem. Copies of function are generated. Each time a call is made to a function, the compiler will generate a copy of the instructions, the code, of the function in the memory of the computer. If you call a function repeatedly, then for each call there will be a copy of the function stored in memory. Let's say a function called alpha with an integer parameter is called 3 times during a program's execution. Int x, y, z. X, y, and z are assigned before the calls are made. Alpha x, alpha y, alpha z. They all have a ... between them. Alpha's code will be copied 3 times in memory as each copy is made for each call. See figure 20.3. Figure 20.3. 3 copies of the function alpha are shown for each call made to the function. Main has alpha x, alpha y, alpha z. Each one individually goes to a copy of alpha. Once the call is made. Whenever a call to a function is made, the compiler immediately leaves the place where it is to go to the place that was called. Recall that this call to a function just needs the function name with any necessary parameters inside. In the main function of the program, there will be an initial call to the factorial function, perhaps followed by an output statement to show that answer on the screen. The initial call is the first call to start the recursive process. After recursion is completed, the next statement here, a cout statement, is executed. Result equals factorial 6. A function is called here. Cout, result, end line. The answer will be on the screen. Once inside the function factorial, the recursive process begins, since the function includes a call to itself. However, this time the call is slightly different because factorial is called with a smaller number and as a parameter. The statement that contains the call will look something like this statement. Answer equals 6 times factorial. Compiler leaves this statement to go to the factorial function. In this statement, the variable answer is assigned to a product, the answer you get when you multiply two numbers. But the product 6 times factorial, which is 5, factorial of 5. But the product 6 times the factorial of 5 cannot be calculated because the computer does not know the answer to the factorial of 5. Before the product can be found, the compiler will leave the function it is in and go to another copy of the function to compute the value of the factorial of 5. We are doing the problem for a second time, but this time we are computing the factorial for a smaller number, 5. See figure 20.4. Figure 20.4. The function is shown with the value that was sent into it, 6, and a copy of the same function is shown with a new, smaller value, 5, that was sent into it. When the second function finishes its work in computing the factorial of 5, it will return a value to the exact place where it was called. The returned value is used to compute the product in the assignment statement. Answer equals 6 times factorial 5. Inside factorial 6. 6 times some value will be assigned to answer. What happens in the factorial function that had 5 sent into it? That function will call it factorial 5. Had its own assignment statement with a call to another function. Consider this statement. Answer equals 5 times factorial 4. Inside factorial 5. It looks like the exact same statement we saw in the first copy of the function, the factorial function, with the parameter 6. Now we are in another copy of the function factorial 5. This statement includes another call to the factorial function, this time with the parameter 4. Let's call it factorial 4. So factorial 4 is called and we expect to see the same kind of statement inside the function as we have already seen. Likewise, factorial 4 has the same assignment statement. Here it is. Answer equals 4 times factorial 3 inside factorial 4. The second last call in recursion. We are almost done with these calls. There are 2 calls left before we reach the stopping state, the end of recursion. The second last call is the call to the factorial function with the parameter 3 sent into it. Let's call this function copy factorial 3. Once you enter the factorial 3 function, you will see the last call in recursion. This is the statement. Answer equals 3 times factorial 2 inside factorial 3. The last call in recursion. Now the last call has been made, and we enter the factorial with parameter 2. Here is the stopping state of recursion. We have encountered a factorial problem whose answer we do know. We do not have to call anything else to get an answer. We have a partial answer to the problem. Answer equals 2 times 1 inside factorial 2. No more calls. Coming back up through a recursive web. I just mentioned that we have a partial answer to the original problem. We need to examine the next stage of recursion to see how we arrive at the final definitive answer to the original problem, computing the factorial of 6. So far, we have just been calling other functions and not getting any results. With the call to factorial 2, we have an intermediate answer, the value 2 from the product of 2 times 1. The way to get the final answer is to check what happens next in each function. Consider this fragment of code from factorial 2. Answer equals 2 times 1 inside factorial 2. Return answer. What happens with the return statement? If you recall, it will cause the value in the variable answer to be sent back to the place that called at. Unlike all of the previous examples where we used the return statement, we were always sending values back to the main function where the call was begun of the program. In this example, we are sending the value back to the previous factorial function, factorial 3. Watch what happens when we look at the statements in factorial 3. Answer equals 3 times factorial 2 inside factorial 3, 2. Return answer from 3 times 2, 6. The value 2 is multiplied by the number 3, since 2 was returned from factorial 2. But wait, after this statement, there is another return statement, which will cause another value to be returned to the place that called it. This time, the value 6 times 6, which is 3 times 2, will be returned to the place that called factorial that called factorial 3. But which function called factorial 3? It was factorial 4 that called factorial 3. And here are two statements from factorial 4. Answer equals 4 times factorial 3 inside factorial 3, 6. Return answer from 4 times 6, 24. The value 6, which was computed and returned from factorial 3, is multiplied by the value 4. Next, the value 24 will be returned to the function that called factorial 4, factorial 5. The same process is repeated inside of factorial 5. Answer equals 5 times factorial 4, 24. Returned answer from 5 times 24, 120. We have almost finished following the compiler back to all the places where calls were initiated to other functions. Now the value 120 will be returned to the function that called factorial 5, which was factorial 6. Answer equals 6 times factorial 5, which is 120, inside factorial 6. Return answer 6 times 120 equals 720. The final statement in the factorial 6 will return the value 720 to the main function, where the first function call was made. Once inside the main function, that value is printed on the screen through the cout statement. Result equals factorial 6, 720. Cout, result, end L. 720 is printed on the screen. This is just one example of how recursion, the process of a function calling itself, is used to solve a problem. Recursive solutions tend to be very quickly computed, but they have the disadvantage of using a lot of memory. Remember that every time a function is called, another copy of that same function, this time with a different parameter, is generated. Note: recursion always involves calls to the same function, with different parameters each time. Another important part of recursion is understanding how the compiler moves from one function to another through the return statement that is used in each function. On the CD, a program written in the C++ programming language that computes the factorial of a number. Summary. This chapter covers the topic of recursion, a method of solving a problem by using a smaller case of the same problem. Functions are used in recursive solutions. As the same function is called over and over again, it is called with a different parameter each time. The value of the parameter is smaller for each successive call, and this is what is meant by a smaller case of the same type of problem. Eventually, a smaller case is reached called a stopping state, and the recursive process ends. After all the calls have been made, the return statement of each function sends the compiler from one function back to the function that originally called it. This chain of recursion is what makes the process sometimes difficult to follow. We recovered two examples in this chapter. The first example was a situation where the meaning of an unknown word was found by repeatedly looking up simpler synonyms for the original word. In the second example, a factorial operation on a number was done by finding the answers to factorial operations of smaller numbers. A factorial of a number is defined as the product of the number and all numbers less than it, down to the number 1.